Humans are natural-born explorers. We charge into uncharted territory and seek out the unknown. We've mapped nearly every inch of Mother Earth and left tracks on the moon. But to set foot on another planet, to travel beyond our solar system, that is a dream for the future. A dream that comes to life in the feature film Interstellar.
We must think not as individuals, but as a species. We must confront the reality of interstellar travel.
The film Interstellar deals with the quest for new worlds and the fate of humanity. Sound like the stuff of science fiction? Maybe. But the foundations of this film are rooted in real science, thanks to the involvement of renowned astrophysicist Kip Thorne.
In Interstellar, one of the most important features is the way that the science is totally embedded in the film. There are some wild things in here.
Beyond fantasy and fiction, this is the real science of Interstellar. Space travel has been a staple of the movies from the very beginning, but the feature film Interstellar has a unique pedigree. It was inspired in part by the work of Kip Thorne, an authority on astrophysics, gravitational waves, and the warping of space-time. He's also an executive producer on the film.
In Interstellar, real science was built into the fabric of the film from the outset. The other major players in this film, they all respected the science, and they worked with me to see that the science was well incorporated.
Can you tell me what the easiest sort of definition of what a singularity is?
Kip and myself meshed well in terms of trying to use current thinking, current scientific understanding to drive the narrative.
The language we use, it's a place where the curvature of space and time gets infinitely high.
So we're good, okay.
And we just hope that the research that we've done, the conversations that I'd had over the years with Kip and that Chris had had with Kip, informed the narrative and that the audience would feel that.
Why simply imagine, fantasize about things that might happen in space or on an interstellar journey? Why not actually look at the real science there?
It's an Indian surveillance drone. Interstellar takes place in a future where living conditions on Earth threaten the survival of humanity.
Now you need to tell me what your plan is to save the world.
We're not meant to save the world. We're meant to leave it.
One of the things that the film explores is, do we belong on Earth and should we be staying on Earth? And if there is anything else out there, should we be exploring that?
Here we go.
In the film, the crew seeks a new place to call home, a planet that can sustain life. Human life.
Am I gonna make it?
Yes, you are.
Sounds like a job for the explorers of tomorrow. But the search for another Earth is happening right now. Astrophysicist Natalie Battaglia is a passionate planet hunter.
I think the only way that we're going to really understand our place in the galaxy is by looking at this broad picture and understanding the diversity of all planets. 20 or 30 years ago, we didn't know of any other planets orbiting normal stars like our own sun.
Natalie has helped rewrite that story as mission scientist for NASA's Kepler Space Telescope.
Kepler's objective is very simple. It's to determine the fraction of stars in our galaxy that harbor potentially habitable Earth-sized planets.
And what makes a planet potentially habitable?
The one ingredient that we think is common to all life forms is this requirement of liquid water. So that's why we look for planets that have rocky surfaces where water could pool and that are receiving the right amount of energy from the star, where the water wouldn't be locked up in a frozen state because the planet is so cold, nor would it be evaporated away because the planet is too hot. We call it the Goldilocks zone, where liquid water could potentially exist.
Launched in 2009, Kepler stared at one small patch of the Milky Way for 4 years straight. Compared to stars, planets are too tiny for Kepler to spot. But it can detect their shadows.
Every planet orbiting a luminous object is casting a shadow out into space. The Kepler spacecraft makes use of that fact, waiting for a planet in its orbit about the star to pass directly between the disk of the star and the spacecraft. And the telescope perceives that as a dimming of light.
This simple method has revealed thousands of exoplanets, planets orbiting other stars in our galaxy.
What we've learned so far is that literally every star in the galaxy has at least one planet. There's an amazing diversity of exoplanets out there. We've found very exotic worlds. 200 light years away, there is a Saturn-sized planet orbiting not one, but 2 stars. So if you were living on a world like Kepler 16b, you would see in the sky 2 stars rising in the east, sitting in the west, continuously changing position as they orbit one another. And this is an artist's rendition of the planet Kepler 10b. It's orbiting 23 times closer to its parent star than Mercury is to our own sun. So this star-facing side is being blasted by stellar radiation, creating temperatures in excess of that required to melt iron. The planet has an entire hemisphere larger than the Pacific Ocean, which is an ocean, but it's not an ocean of water. It's an ocean of molten lava.
Not an attractive destination. But Kepler recently found us a possible second home.
This is an artist's concept of the Kepler 186 planetary system. 5 planets orbiting this M-type star, and the outermost planet is Kepler 186f. Our first discovery of an Earth-sized planet in the habitable zone of a normal star. When I think about Kepler 186f, I try to imagine it as a real place, because it is a real place. We know that it could be rocky. It's the same size as Earth, so I do imagine a rocky surface. We don't know that it has a liquid ocean, but we can certainly imagine one. And then, all of a sudden, in your imagination, you internalize the existence of this world out there, that there is a place that could be very, very much like Earth.
So, when do we set sail for these distant shores? Reality check. Kepler 186f is nearly 3 quadrillion miles from Earth. Otherwise put, 500 light years away. That's a journey of 500 years at the speed of light. But no thing can travel as fast as light. At best, our spacecraft are thousands of times slower. Even the spaceships in Interstellar don't come close. So how do they reach new worlds beyond our solar system? They take a walk on the warp side of space and time. The Science of Interstellar.
You have no idea when you're coming back.
Couldn't you have told her you were going to save the world?
No.
I'm coming back.
When we journey to a far-off place, we travel not just in space, but also in time as we move into the future. Until about a century ago, scientists believed that space and time were entirely separate. Theoretical physicist Sean Carroll explains how Albert Einstein overturned that idea.
One of Einstein's great insights was that space and time are related to each other. Where you have space and you have time, Einstein says, actually there's only one thing, which we call space-time. And then he says this space-time thing, it's not just the stage on which all the action plays out. It's an actor itself. Space-time can change, it can move, it can bend, and it can warp.
Einstein's theory of relativity states that space-time is like a flexible fabric. The objects embedded in it, the sun, planets, even us, warp that fabric. And a consequence of that warping is what we call gravity. The more massive the object, the more space-time is warped, and the greater the gravity. We feel gravity. The flexibility of space-time is harder to grasp on a gut level, but its effects are measurable. As Sean demonstrates, the greater the gravity, the more slowly time flows.
For example, if I were on the ground floor with a clock, a super accurate atomic clock, and a twin of mine was up on the top floor of a building with an equally accurate atomic clock, if we later on compared them, mine would have ticked off fewer seconds.
On the ground floor, Sean experiences slightly more gravity than his twin on the top floor. He also experiences slightly less time than his twin. The difference is tiny, but real. And there are practical applications.
For example, the GPS system, the Global Positioning System, that is a very, very precise set of clocks on satellites orbiting around the Earth. And that orbit is in a slightly different gravitational field than we are in down here. So the fact that time moves differently here on the surface of the Earth than in the satellite orbit is very, very important to getting the GPS to work correctly.
Time on a GPS satellite clock advances faster than a clock on Earth by about 38 microseconds per day. So the system's computers correct for that. Motion also affects our experience of space-time.
The best way to say it is just staying still means that you experience the most time that you can. Moving around and doing things means you experience less time.
Let's revisit Sean at the wheel of his car and his twin on a park bench.
If you move out on your car and then you come back, compared to the person who stayed behind, your clock that you took with you on that journey will have experienced a little bit less time than the one who stayed behind.
We normally move too slowly to notice the effect. But if Sean could drive near the speed of light, he could race across the United States and back again 1,000,000 times and experience less than a second of time, while the twin he left behind would endure hours of waiting for Sean's return. In other words, Sean would have traveled into the future compared to his twin. This means things may get tricky in years to come as we build faster spaceships. The closer we get to the speed of light, the more out of sync we'll become with those we leave behind. But the warping of space-time may also provide shortcuts that could make interstellar travel a snap. Wormholes. They're a staple of science fiction, but they're based on real science.
Einstein's relativistic laws govern the warping of space and time, and they say that wormholes might exist, they could exist. So this dates all the way back to 1916.
A wormhole is a particular way that space and time can be curved. It's like adding a little tube that connects two parts of space.
The basic idea is that if you're an ant and you live on the surface of the apple is your entire universe. You can go around the outside through the universe itself, or you can go through the wormhole.
But Einstein's equations also predict that if wormholes do form in nature, they may be subatomic in size and exist for only fractions of a second before closing off. Theoretically, what would it take to keep a wormhole open and make it big enough to accommodate a spaceship?
It turns out that in order to hold a wormhole open so it doesn't crunch off and kill you when you try to go through, that you have to have the wormhole threaded by a negative mass or negative energy. Einstein says mass and energy are equivalent.
Almost all the forms of matter we know have positive mass and exert gravity. Negative mass would exert anti-gravity and repel the walls of a wormhole to keep it open.
Strangely, it is true that negative energy can exist, and it's been created in the laboratory, but only in very tiny amounts.
It would take vast quantities to prop open a wormhole large enough for a spaceship. But just maybe, in the future, engineers will devise advanced technologies to do just that.
Today, it's an educated guess, maybe I should say a half-educated guess, that wormholes cannot exist in our universe, but we're far from sure of that.
The truth is we just don't know right now. We don't understand the laws of physics well enough to say for sure whether or not wormholes are possible.
But since they're not impossible, they're fair game for a filmmaker.
I was very excited about the idea of focusing on a family who would be the pioneers, who would experience some of the extraordinary features of astrophysics, particularly the idea of a wormhole that would allow us to travel to distant stars.
To create a wormhole based on real science, visual effects supervisor Paul Franklin turned to Kip Thorne.
The popular image of what a wormhole might look like is literally just a hole in space. Generally, it sits on an invisible surface. You can see stuff sliding down the sides and disappearing down the drain, as it were. And right in that first conversation, Kip showed me an image of that kind of classical fantasy image of these things and said, this is all wrong. This is not how it is.
Kip worked out the scientific equations that define the wormhole and sent them to Paul's animators back in London.
And so for the movie, I built a mathematical model of a wormhole based on Einstein's relativity equations.
Paul, Kip, and myself would discuss, okay, we'll visualize the thing, we'll simulate the thing exactly as the calculations say. And Paul Franklin and his team, they were thrilled to get algorithms that were the absolute latest, most interesting and up to the minute.
Now we go to the other one.
Well, the wormhole is a three-dimensional hole in space. And what do you get if you take a circle and sweep it out in 3 dimensions? You get a sphere. So the wormhole almost feels like a crystal ball hanging in space.
I don't think anybody had ever really done this kind of visualization before. This is really unique. First time for me, as well as for you and the audience.
Absolutely, yes.
In Interstellar, crew members take a giant leap of faith when they plunge into a wormhole.
You can't just think about your family. Now you have to think bigger than that.
I am thinking about my family and millions of other families.
Beyond that wormhole, the crew will enter the realm of the most extreme objects in the universe. Black holes. The Science of Interstellar. From Earth, a starry sky may seem a realm of timeless calm. But when we aim our most advanced tools at the universe, they capture displays of monstrous power and violence. Galaxies collide. Cosmic clouds of gas and dust spew radiation. Stars explode, then die. For a filmmaker, space is full of dramatic possibilities.
When you venture out into a story about a man against the elements, when that journey is interstellar, the possibilities for visualizing the threat against our protagonist become very much more exotic. You know, deep, deep space. It gives you a very, very fresh approach.
Exactly.
One of the greatest challenges for a crew on an interstellar voyage will be to navigate the dangers of black holes. Black holes were predicted by Einstein's equations, but physicists questioned whether they could really exist.
A black hole is a strange beast. If this were a black hole, then instead of a rubber surface, it would have a surface that is made of absolutely nothing except warped space and time. It's a place where gravity is so strong that if anything falls into the black hole, it can never get back out. If you fall in, you can't send signals back out. Light can't get out from the interior.
So you might ask, how would that ever happen? In outer space, you can get so much mass together, like in a supermassive star, that the gravity just becomes stronger and stronger and stronger, and eventually the pressure that matter exerts on itself can't keep up. And everything collapses, there's a big explosion, some of the stuff is blown away, but the rest of it collapses into a black hole.
A black hole that spins on its axis drags the very space around it into a whirling motion that pulls stars and planets into orbit. Closer in, gravity increases like a riptide. At a boundary called the event horizon, gravity becomes so extreme that nothing can escape being pulled into the heart of the beast and lost forever.
Black holes are simple, and yet they have a lot of character. It's almost like they can take on personalities. They can be picky eaters. They can be energetic. And what you're seeing and describing is really how the black hole interacts with the environment.
UCLA astronomer Andrea Ghez
Looks like this is Sagittarius star.
is an expert on black hole detection.
I think it's that one there.
She played a key role investigating what had long been a scientific hunch, that a huge black hole lives at the center of the Milky Way.
It's looking good.
Astronomers knew the heart of our galaxy was buzzing with gas, dust, and millions of stars. Some powerful force appeared to be driving this hubbub. Could it be a black hole? Ground telescopes just couldn't produce sharp images of the region. Then a technique called adaptive optics vastly improved the view.
So this is what looks like before you use any advanced technology. It's a blurry mess, and now you can see the individual stars with adaptive optics turned on. So each point of light here is associated with an individual star.
Andrea put that technique to work at the Keck Observatory in Hawaii.
This is a road map.
And she and her team began to track the stars at the center of the Milky Way.
And that's the center of our galaxy. The very first year that we took the data was in 1995. Then we go back to the telescope in 96. Then we take our second image. And you have two pictures, and you can compare them.
Andrea wanted to see if the stars were orbiting a single source of gravity. But stars can take years to complete an orbit.
So it was really important that we kept going. And by 2000, we finally started to see the stars curve. In other words, the gravitational influence of the black hole had made those stars go from straight lines to starting to bend. Measurements were precise enough to see that curvature.
Year by year, Andrea and her team built their case.
This animation represents 20 years of work, and it tells you that there is a black hole and exactly how massive it is.
Andrea's painstaking project revealed a monster with more than 400 million times the mass of our sun at the center of our Milky Way. Today, scientists are hunting black holes with new tools. Caltech astrophysicist Fiona Harrison scans the skies with NuSTAR, a telescope that looks at the universe in high-energy X-rays.
The black hole itself doesn't emit light, but dust and gas falls onto the black holes, and in doing so, it heats up, and it emits X-rays.
NuSTAR captures black holes in the process of feasting on matter, and the telescope is spotting them all over the place.
It's really only 10, 20 years ago that we thought black holes were rare. We now know that every galaxy, like our Milky Way, has a massive black hole at its heart. So rather than just being curiosities, they're actually fundamentally important to why the universe is the way it is.
So, is the Earth at risk of getting swallowed by a black hole?
Even though we have black holes sprinkled throughout the galaxy, we're in absolutely no danger. It's a common misconception that black holes might suck the Earth. Well, there's no sucking going on. It's just normal gravity. It's just when you get very close to it that there's a region from which light can't even escape, and Earth is not going to do that.
But what if a spaceship had a close encounter? What if an astronaut dove in feet first?
In the simplest descriptions of this, the descriptions that you will find in most books that you read, you're simply stretched from head to foot and squeezed from the side by tidal forces, spaghettified, as one often says. You're spaghettified as you fall in, and you're destroyed. That's the standard story.
The truth is, all the laws of physics that we know break down in the heart of a black hole. Physicists are still working on exactly what happens there.
That's the gravity well, though, isn't it?
When we talk to non-physicists, we will often say it's the gravity well.
So you've been lied to us all these years.
You know how these things go. There are lies and there are lies.
I know, but now.
The movie Interstellar deals with physics that is well understood, well established. It deals with physics where we make educated guesses and we're almost sure but not 100% sure of our guesses. And it deals with physics at the frontiers of human understanding where we have to speculate. And when you get beyond those frontiers, Interstellar works hard to align itself with the best speculations that scientists could imagine.
Interstellar mines that gray area where new ideas percolate. and taps deep into questions about the nature of the universe. The Science of Interstellar. In Interstellar, telescopes on Earth first detect the presence of a wormhole. It shows up as a gravitational anomaly that distorts the view of space.
We made the wormhole not have all that strong a gravity.
But why wormhole? Because then you have a reason for your trip around it.
I feel uncomfortable with the wormhole having that much gravity. When I first began working with Christopher Nolan, he wanted a wormhole that had rather gentle gravity. We discussed how big the wormhole should be and agreed that it should be just barely big enough that it could be seen from Earth through the bending of light around the wormhole by the wormhole's warped space.
Kip Thorne worked out just the right gravity for Interstellar's wormhole, using equations based on Einstein's theory of general relativity. As we've learned, that theory states that objects warp space-time, creating gravity. It also predicts that when objects move, they generate a pulse that propagates through space-time a bit like waves through water. These gravitational waves have never been directly observed. They would be small and hard to detect, unless they were generated by massively violent motion, like the birth of the universe. Physicists developed their Big Bang theory in part by observing that today the universe is expanding. Galaxies are moving away from each other like raisins in a rising loaf of bread, which suggests that in the distant past, the universe must have been much smaller.
If you wind the movie backwards, in the past, everything was closer together. And you plug that idea into the equations that Einstein gives us. And there's a moment, which we now know is about 14 billion years ago, when everything was on top of everything else, when the density of stuff in the universe was apparently infinitely big.
Then a powerful force triggered an expansion of space itself, faster than the speed of light, a theory called cosmic inflation.
And the theory said that this inflation should have taken fluctuations in the shape of space and amplified them so they got much stronger. And they become gravitational waves, producing ripples in the fabric of space and time.
If we could detect those ripples today, it would help us understand how the Big Bang banged.
The trick was always, how are we going to measure such a thing? And that led us to propose and develop this very specialized experiment, which one of my colleagues referred to gleefully as a wild goose chase.
Caltech physicist Jamie Bach works in experimental cosmology.
Experimental cosmology is building experiments, trying to get back to the dawn of time. You need a hand on that?
The focus of his latest experiment was the oldest light in the universe, the faint afterglow of the Big Bang. Physicists have mapped this cosmic microwave background across the universe. If the birth of the universe produced gravitational waves, they would have warped this primordial light and caused it to be polarized or curled in a specific direction.
If one could measure that polarization, and then not only measure it, but look at its pattern, there might be a kind of a swirly pattern that would be an indicator of gravitational waves.
Jamie and his team designed a series of small, super-sensitive telescopes that they installed where the skies are crystal clear at the South Pole.
The South Pole is the closest we can get to outer space to make our measurements.
For 8 years, the team's telescopes scanned a patch in the sky, measuring minute differences in the temperature of the cosmic microwave background, and a pattern emerged.
Our results reported that we see this swirly pattern of polarization that's consistent with what you expect from gravitational waves.
So they didn't really see the gravitational waves from the early universe, but they saw this polarization pattern that was precisely what was predicted, except that it was stronger than expected. It tells us what went on immediately after the Big Bang, when the universe was a trillionth of a trillionth of a trillionth of a second old. So it's seeing almost the creation of the universe.
The finding must be confirmed by other experiments. If it holds up, this will be the first evidence for detection of the gravitational waves predicted by Einstein. To contemplate the mysteries of space, time, and the universe can make a person feel mighty small. Maybe it's best to lower our sights, hunker down, and focus on planet Earth. But that's not really an option for humanity in the long run. Interstellar depicts a future where living conditions on Earth are grim. There's only one solution.
Now you need to tell me what your plan is to save the world.
We're not meant to save the world. We're meant to leave it.
The Science of Interstellar. This blue oasis is the only place we know that supports life. But that could change in a flash. February 15th, 2013. A meteor shining brighter than the sun streaks across Siberia. It's a rock 65 feet in diameter, and when it explodes in midair, it releases more than 20 times the energy of the bomb dropped on Hiroshima. No one was killed, but more than 1,000 people were injured. Asteroids have struck Earth before. Some 65 million years ago, a monster 6 miles wide may have wiped out half the species on Earth. Remember the dinosaurs? A similar impact, or worse, could happen any time and turn our blue marble into a lifeless rock. In the meantime, perhaps a greater threat to the planet is us. And the bottom line? Earth cannot sustain us forever. In a few billion years, our sun will expand as it begins to die. And our planet will be toast. But there's good news. Unlike the dinosaurs,
flight crew, close and lock your visors, time to fly.
we can leave Earth.
T-minus 10.
9. Ignition sequence start.
6.
5.
4, 3, 2, 1, 0.
Zero and liftoff of Space Shuttle Atlantis.
To date, nearly 600 people have traveled to space. During the shuttle era, Marcia Ivins made the trip 5 times.
In order to record all of this, we have created this wiring nightmare here.
At Kennedy Space Center Visitor Complex, she checks in on an old friend.
I look at Atlantis hanging here. It's a surreal kind of experience to think, I flew that into space. It's still something that I have a hard time believing. Hi.
My name is Jenny.
1, 2, 3.
And it makes me feel good that people still have a wonder and an amazement and a pure joy for the fact that we did fly this vehicle into space.
For Marcia, each mission was as breathtaking as her first.
I looked up overhead, and here was this black sky and this blue Earth. All hits you at that point. I am not on the planet anymore. And every astronaut who has flown has come back and said the same thing. As you circle the Earth, you do not see natural borders and boundaries that separate the countries. And all of the wars and the angst and the strife that tear this planet apart seems so insignificant from that view.
To me, space travel, space exploration has always represented the ultimate frontier. It's at the absolute extremities of what human experience is, and it's all about trying to in some way define our place in the universe.
40 seconds away from the Apollo 11 liftoff.
I remember growing up as a kid, and we were both fascinated by this impulse to flight, this impulse to build unimaginable machines and use them to blast off into space.
Having fired the imagination of a generation, pulls into port for the last time.
The space shuttles were retired in 2011 after traveling more than 500 million miles. Space exploration demands enormous resources, the kind that government agencies like NASA can marshal. Recently, some new players entered the fray.
I do think we're at the dawn of a new space era, and it's one where commercial companies play a much stronger role. NASA's not out of the picture. They're very much in the picture, but it's not all a NASA-designed system.
In 2002, Elon Musk started his own rocket company. A decade later, under contract to NASA, SpaceX became the first private company in history to carry supplies to and from the International Space Station. Now, SpaceX is tackling an even greater challenge.
I started SpaceX with the idea of trying to revolutionize space transport. And critical to that is full and rapid reusability of the rocket. The big issue with rocketry today is you get one use out of the rocket, and then it smashes down into the ocean or into the plains of Siberia, and you can't use it again. If you can, in fact, land the rocket safely and then reuse it with a minimal amount of effort, then you can dramatically reduce the cost of space transport.
SpaceX is currently developing a fully and rapidly reusable launch system, and that will take Elon closer to a more ambitious goal: to help send crews to establish a colony on Mars. Not a mission for the faint-hearted.
Anyone who wants to go to Mars, their desire for adventure would have to overcome their desire for comfort and safety.
A colony on Mars could be the next giant leap for humankind.
It's such a fundamental idea when you think about it. It's just a decision that has to be made in terms of how you view the human race's place in the universe. We either stay here on Earth, or we leave and journey through the galaxy.
We'll find a way. We always have.
The Science of Interstellar. To create the look of the space technology in Interstellar, Christopher Nolan took a clear design approach.
We didn't want to have anything that felt purely decorative. We wanted to approach it from a much, much more functional point of view. Just be as convincing as possible, looking at the NASA technology that exists today, the International Space Station, these kind of things as our influences.
There's no telling how space technology will evolve in years to come. We may be decades away, or longer, from establishing a colony on Mars, or a permanent habitat in orbit around the Earth. But people around the world are dreaming of that next step. At a recent space conference, NASA and the National Space Society handed out awards to dozens of forward-looking designs. A self-sustaining settlement for 20,000 people. A moon base that mines minerals from lunar soil. A fleet of robots that clean up space junk.
But of course, this is really hard because we're burning fuel.
There's not a single PhD among the prize-winning designers. These are middle and high school students from around the world. One of these kids may stand on Mars someday, or make a breakthrough in propulsion systems, or start a revolution in astrophysics. To inspire their kind of enthusiasm is the hope of the Interstellar team.
I would love for kids to watch and get excited about the possibilities of space travel and exploration.
I would hope that this film introduces many people to science who might not have gotten curious about this kind of science in any other way.
I think it would be really thrilling if people got some sense from this film that these ideas are worth thinking about.
The interplay between science and science fiction springs from a deep-seated creative drive to make sense of the unknown, to engineer new worlds, to dream up a better future. We'll find answers where we always have, just beyond the next horizon.
What first inspired me was the sky, the stars, the moon, the planets.
Thinking about going to space is really exhilarating.
I've always wanted to know, like, what's next, and for me, space is next.
What we can do is beyond our imagination.
For the survival of the human race, really, the only option is to go into space.
It should be something that a first step we should take as a world and as a planet.